Hello everyone, I am continuing with my convergence and divergence of series, and this is my lecture 2. Let me do the problem that I have written on the board. See, this is the first problem wherein you are given, see actually this is a series. In this series runs from n is equal to 1 to infinity. Now we have to decide or we have to test whether this series an, that is sigma of an, to test whether sigma of an is convergent or divergent. See this one. You have to test given an. Right? What is your an now? An is equal to log of n plus 5 minus log of n plus 2. So this is nothing but, see, this is log of n plus 5 divided by n plus 2, because this is log a minus log b is log a divided by log b. So here you see that I can write this as log of n into 1 plus 5 by n into 1 plus 2 by n. So this is equal to, this is log of 1 plus 5 by n divided by 1 plus 2 by n. So this is what we have. Therefore, limit of n tending to infinity of an is equal to log of limit n tending to infinity of 1 plus 5n divided by 1 plus 2n. But this is 0. See, 1 by infinity, limit infinity tending to n tending to 0 is 1, 0. So this will be equal to log of 1 by 1. This is 0 and this is also 0. Log of 1 is equal to 0. Because the series is approaching or it is becoming 0, this implies that sigma an is a convergence series. So this is a convergence series. So this is a convergence series. So how it is done? See, take this. This is log of a by b. Then take this n outside and bring it to the form. When you are doing it, bring it always to the form of some a by n, so that you see that when n tends to infinity, that a by n tends to 0. So I bring it to that form, and naturally this n and n will get cancelled. Now you apply the limit as n tends to infinity. This is 0 and this is 0. Therefore you are left with log of 1. But log of 1 is 0. So this series approaches a definite limit, that is 0, and therefore this series converges. So this is how we do this. And see, so this is my first problem. The second problem is see, what is this? Given an is equal to 1 plus 5 by n to the power of 2n. And find whether the limit exists. Limit n tending to infinity of an is equal to limit n tending to infinity of 1 plus 5n to the power of 2n if it is equal to L if it is equal to L, then a finite value, then sigma of an is a convergence series. Otherwise it will not be correct. So what I want to say is that, see, an is given, applying the limit as n tends to infinity, if I can prove that this is taking a definite value, this is taking a definite value L, which is a finite value, then I can say that sigma of an is a convergence. But in case it tends to 0 or minus, tends to infinity or minus infinity, then I will say that the series is a divergence series. Let us test whether how, see, if some manipulation is required, a mathematical manipulation, then we can carry out the limit as n tends to infinity and determine whether the series is as defined by this an is a convergent or a divergent series. Okay, now see, let me write it in such a way that I am able to find it. Okay, see what I do here. So I rewrite this in such a way that 1 plus, this can be written as n by 5 whole to the power of 2n, and I do some adjustments and write. See, this is this 2n, how I write this is, here you find this is n by 5 multiplied by 10. So this gives you again, so I am not changing anything. I am not changing anything. I simply rewrite in such a way that I will be able to identify it as some series. So I write this as n by 1 by n by 5 is equal to 1 plus 1 divided by n by 5 whole to the power of n by 5 multiplied by 10. I take this n by 5 is equal to n. Now you see that as n tends to infinity, this infinity by 5, that is n by 5 also tends to infinity. Therefore, this n capital N, which I have taken to be n by 5, will also tend to infinity. So this capital N tends to infinity as small n tends to infinity. And therefore, what is that you get now? So an is equal to your 1 plus, it is 1 by, it is n, 1 by n whole to the power of n. See, whole to the power of, I will write it as, see, it is equal to your, see, 10n. It is n by 5 is fine, so 10n. So this is 1 plus 1 by n whole to the power of n whole to the power of 10. Now you see that this an limit of n tending to infinity, an is equal to limit of n tending to infinity, see I have written here, see, n tending to infinity of 1 plus 1 by n whole to the power of n whole to the power of 10. But we know that this is an exponential series. 1 plus 1 by n whole to the power of n, as n tends to infinity, is e to the power of 10. As 1 plus 1 by n whole to the power of n is equal to e, as n tends to e. Okay, so this is equal to e to the power of 10, which is a finite value. Therefore, sigma of an converges. So this is a convergence. So this is what we get. So this is also correct. So what is that I do here? I do a small manipulation so that I will be able to identify this with a series, known series, which is exponential series. I bring it in exponential series form. Now you find that I am able to get the value of this series as n tends to infinity as some e to the power of 10, where e is a well-known number to us, incommensurable number, and therefore e to the power of 10, which is a finite value, and therefore this is a convergence series. Okay. Now let me take one more two problems here. Here you have got here. See, this is, now we have to test the convergence of this. See, what is your an now? As n tends to infinity, we have to find whether this is a convergence series. See, for this I will take this to be 5 to the power of n divided by 3n plus 10. So what is your an plus 1? It is 5 to the power of n plus 1 divided by 3 to the power of n plus 1 plus 10. Okay. Now you see that this an I am using, see, another method is also there, but I am using D'Alembert's method. So you see that you get an plus 1 divided by an is equal to 5n plus 1 divided by 3n plus 1 plus 10 into, if you divide, you will get this to be 3n plus 10 divided by 5n. So this will be equal to, you see that this is nothing but 5n means 5, and here if you take this 3n, it is a 5n will go off, giving you 3n into 3 plus 10 by 3n multiplied by, you take this 3n outside, 1 plus 3n. Now you see that we have got this 3n and 3n will go off. So an plus 1 divided by an will be equal to, it is 5 into 1 plus 10 divided by 3 to the power of n, 3 plus 10 by 3 to the power of n. Now limit of n tending to infinity of an, see, this is again 0, because n tends to infinity is a huge number, that this will become 0 and this will also become 0, this becomes 0, this becomes, so you will get 5 by 3. Now this 5 by 3 is equal to L, which is greater than 1, and therefore the series an is a divergence series as D'Alembert's ratio test, as per D'Alembert's ratio test, limit of n tending to infinity of an plus divided by n, L less than 1 convergence series, L greater than 1 divergence series. See? So what is that I have done here? See, I have taken this 5 to the power of n plus 1, this is given to you. I take this an plus 1, but an plus 1 is wherever n comes, you put it as n plus 1. Now, I am going to use what is called D'Alembert's ratio test. This I have already done. That is why I am using it as DAR test. What is D'Alembert's test? D'Alembert says that if you take limit of n tending to infinity of an plus 1 divided by an, and if it is equal to L, and if L happens to be less than n, then the given series is a convergence series. If it is greater than 1, the series is a divergent series. Now, I am going to apply D'Alembert's test to my problem and see whether the value that I am going to get is less than or greater than 1, so that the convergent and divergent will be as the case may be. Okay. Now, Here you see that an plus 1 divided by an. I do the simplification here and I do some manipulation to see that get rid of this 3n. 3n goes off. Here 5n and 5n goes off. So you are left with 5 and 5 into 1 plus see 1 plus 5 into it is 1 plus 10 by 3 to the power of n, and here 3 plus 10 by 3 to the power of n. You allow this n to 10 to infinity. When you allow this n to 10 to infinity, this becomes 0 and this becomes 0. So you are left with 5 by 3. But this limit an is equal to an. See, limit of an as n tends to infinity is now it is equal to 5 by 3, which is L, which is 5 by 3 greater than 1. And as per D'Alembert's test, see, as per D'Alembert's test, limit of an plus 1 an is equal to L, and L is greater than 1. Here L is, therefore L is less than 1 means convergent, L is greater than 1 means divergent. Here you see that this is L is greater than 1, therefore this is a divergent series. Okay. So this is a problem in this. Now let me come to the last one here. So this is also for divergence series. Let me come to this. Given an is equal to your n factorial divided by n to the power of n. Now you see that here again there are various ways of doing it. We have to find as n tends to infinity is convergent or divergent. So you see that this is, see, 0, I will put it like this, 0 less than or equal to, this is nothing but 1 n into n minus 1 into n minus 2 dot 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 3 to 1 divided by n into n times. See 1, that is 1, divided by 1, see n times. So this is nothing but n by, see, it is n by n into n minus 1 by n into n minus 2 by n and dot 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 it goes up to 3 divided by n, 2 divided by n, this is 1 and this is less than or equal to 1 by n. So this is less than or equal to, so you see that this is n by n, if you multiply n minus 1 by n will be still less, n minus 2 by n will be still less, you see that it will be going like this, but 0 less than or equal to this, and if you call this as your Bn and you call this as your An and here you call this as your Cn, this is your Cn, this is your An and this is your Bn, we find that Bn is less than or equal to An, which is less than or equal to n, and as n tends to infinity, Cn tends to 0. Cn tends to 0, therefore limit of an, here this is your an, this is your an, so limit of, therefore limit of n tending to infinity of an is equal to 0, which is when it tends to a finite limit, this is a finite limit, and therefore the series is convergent. So this is one way of doing it. I will explain this. Take this an is n factorial by n to the power of n. This is nothing but 1 into 2 into 3 into up to n, and this is n into n into n times, and divide this n, see n by n, n minus 1 by n, n minus 2 by n, like that it goes on up to 1 by n, and this value is definitely greater than 0, therefore 0 less, or it can be equal to 0. So 0 less than or equal to this, which is less than or equal to the greatest value 1 by n. Now you allow this n to tend to infinity. So this is, you take a call it as Bn, and this is our An, this is our An, and you call it as Cn. Now if you allow this n to tend to infinity, this becomes 0 and this is also 0, that you find limit of n tending to infinity is an is equal to 0, which is a finite value, and hence the series is. So this is a convergence series. This is method 1. This is method 1. Let me teach you the other method of doing it. So this you can do by like this, or the other one is, see, other one, method 2. I will apply D'Alembert's method. So fine, what is your an now? N factorial divided by n to the power of n. An plus 1 is equal to n plus 1 factorial divided by n to the power of n plus 1 to the power of n plus 1. Therefore, let us apply D'Alembert's ratio test. That is, limit n tending to infinity of an plus n is equal to L. L less than 1, convergent. L is greater than 1, divergent. So this is what you will get. Now what is that? Now an plus 1 divided by an is equal to n plus 1 factorial divided by n plus 1 into n plus 1. Now if you divide this n to the power of n will go to the top, divided by n factorial. So you see that this is n factorial, so this is nothing but n factorial into n plus 1 into n to the power of n divided by n plus 1 into n plus 1 into n factorial. So this and this will go off. Here n plus 1 and this one will go off, leaving you with n to the power of n divided by n plus 1 to the power of n. So this is equal to n to the power of n into, so n to the power of n divided by, take this n to the power of n outside, 1 plus n whole to the power of n. So this is what you get. So this, take this n to the n outside, so is n to the power of n into this. So this is equal to 1 plus 1 divided by 1 plus 1 by n whole to the power of n. So call it as 1. Call it as 1. Now this is our E exponential series. Since limit of n tending infinity of this value is known to us. So you see that this is nothing but, so this is 1.1 divided by 2 point something will have. So this is a finite value. See, L has a definite value itself, incoming 2.78 something like that you will have. So you see that E value. So this is the E value. So this is equal to 1 divided by 2.71828. So this is less than 1, and therefore so this is also in this way also okay. So what is that I have done here is that I have taken this, I have taken an plus 1, and if I take the an plus 1, it is n plus 1 factorial. This is n into n to the power of n plus 1 to the power of n plus 1. Then I take an plus 1 divided by n, because of which I am getting this result. That is, I will take this, see, on simplification I will get 1 divided by 1 plus 1 by n whole to the power of n. Now if I apply the limit n tends to infinity, then n tends to infinity of 1 divided by this, but this is nothing but my exponential series e, and this is an incommensurable number whose value is 2.71828. Therefore 1 divided by this is less than 1, and as per D'Alembert test, what does D'Alembert say? That is, if an plus 1 divided by an, if n tends to infinity, is a finite value and is less than 1, we say that the series is a convergent series. We find that this is less than 1, and therefore hence this an must be a convergent series. Okay, please say I will do more problems in the coming days. Do not fail to subscribe for my channel. You will see, you are going to watch many more videos which are going to be definitely useful to college, school level or college level or engineering level students. Okay, thank you.